Welcome to the flight levels. Have you ever wondered how air traffic controllers keep planes from stacking up like a traffic jam in the sky? A key tool controllers use is speed control. Today, we're diving into exactly how controllers assign speeds, the different types of speeds planes use, and where things can get tricky. Stick around because by the end of this video, you'll have a whole new appreciation for the ballet of air traffic. If you're enjoying this content, hit that like and subscribe button. It seriously helps me make more videos like this. Now, let's get into the nitty-gritty of how it all works. First up is ground speed. Ground speed is the speed of an aircraft flying over the ground. Okay, duh. Air traffic controllers have a readout of the ground speed of each aircraft they are controlling. Do aircraft transmit their ground speed to ATC? No. The air traffic computers simply measure the distance an aircraft flies within a set period of time. This simple calculation is processed each time an aircraft's position is updated on the radar screen. Next is true airspeed. This is the aircraft's speed relative to the air it's flying through. The relationship between ground speed and true airspeed is where wind comes into play. Imagine a plane flying from Dallas to Houston. Air traffic control sees its ground speed as 130 knots. What they can't see is that it's getting a 10-knot push from a tailwind. The plane's true airspeed is actually 120 knots. So true airspeed plus tailwind equals ground speed. If the airplane were to make a 180-degree turn in the other direction, the airplane stayed at the same 120 knots true airspeed, what ground speed would the controller observe? Would they see 120 knots, 115 knots, or 110 knots? Let's take a closer look. We started with the true airspeed of 120 knots and added the 10 knots of tailwind to get 130 knots. In the other direction, we will start with the same 120 knots of true airspeed. Now we just subtract 10 knots of headwind to get a ground speed of 110 knots. The last key speed is indicated airspeed. You'd think your airspeed indicator would show your true speed, right? Well, it does, but only at the specific density of air at sea level. The problem is air density changes with altitude and temperature. That's why your airspeed indicator is only accurate at one specific air density. The higher you climb, the less dense the air gets. I like to think of indicated airspeed not as speed, but as a measure of how many air molecules are hitting the front of the plane. Imagine a plane flying at 120 knots true airspeed at 1,000 feet. Now, let's have it climb up to 10,000 feet, still flying at the same true airspeed. Because the air is thinner up there, fewer air molecules are hitting the plane, so the indicated airspeed would be lower. Here's why it's so important for controllers. If a plane is flying at a constant indicated airspeed, say 100 knots, and it descends, its true airspeed will actually decrease. Why? Because the air gets more dense as you descend, so it doesn't need to fly as fast to keep the same number of air molecules hitting it. The opposite is also true. If a plane climbs at a constant indicated airspeed, its true airspeed will increase. This is a crucial concept for what comes next. So, why are we talking about all of these speeds? Because air traffic controllers primarily assign speeds using indicated airspeed and Mach number. True airspeed is not used because back when these rules were made, pilots didn't have a reliable way to constantly calculate it. For low altitude flights, controllers use knots. But at higher flight levels, they switch to Mach, or a percentage of the speed of sound. For example, Southwest 123 maintained Mach 7.8. That would mean the pilot needs to fly at 78% the speed of sound. Mach is used at these higher altitudes because it's a better way to measure the aerodynamic performance and limitations of jet aircraft. Now for the fun part, putting it all together. The most common reason controllers use speed control is to space out planes for arrivals. When I worked the arrival sectors into Denver, we would feed a steady stream of jets to the TRACON. By the time planes left my sector, they needed to be at a specific altitude and speed, such as flight level 190 at 250 knots. And here's the kicker. It's not as easy as it sounds. Modern jets are incredibly efficient and don't have a lot of drag. If you waited too long to tell a pilot to descend, they might not have enough distance to slow down and hit that crossing restriction. Pilots will sometimes say unable to a clearance if they can't meet both the altitude and speed. They can either hold altitude to slow down or descend faster at a higher speed, but they can't always do both simultaneously. When traffic is light, controllers can give pilots the crossing restriction early and let them manage their descent. This is a win-win because pilots can stay high longer, which burns less fuel. But when things get busy, controllers have to be very strategic. Let's walk through a common scenario. Imagine two planes 10 miles apart at cruise altitude, both flying at 250 knots indicated airspeed. We tell the first plane to descend. A minute later, we tell the second one to descend. Even though both are holding the same indicated airspeed, the leading plane's true airspeed will be consistently lower because it started its descent earlier and is at a lower, denser altitude. This means the planes will compress and get closer together. The opposite happens during a climb. If two planes are climbing at the same indicated airspeed, the one in the lead, which is higher up, will have a higher true airspeed and the distance between them will increase. Controllers need to manage this compression and expansion to maintain separation. As pilots receive speed instructions, what are the expectations for them to comply? Do pilots need to be spot on their assigned speeds? Pretty close. Per the Aeronautical Information Manual, pilots are expected to fly their assigned airspeed plus or minus 10 knots. If assigned a Mach number, then their assigned Mach number plus or minus 0.02 Mach. Speed assignments can be as simple as a single speed, such as Delta 1582, maintain Mach 7.5, or it can be an upper or lower speed limit, such as Spirit 721, do not exceed 280 knots, or American 11, maintain 290 knots or greater. Once the requirement for a speed is no longer needed, controllers will instruct pilots to resume normal speed. In the end, controllers use a combination of vectors and speed assignments to choreograph the flow of traffic in the sky. It's a constant balancing act of altitude, speed, and spacing to keep everyone safe and on time. Have you ever had a speed assigned to you by ATC? Let me know about your experience in the comments below. If you enjoyed this video and want to dive deeper into the world of air traffic control, be sure to like, share, and subscribe so you don't miss my next video. Be sure to visit flight-levels.com, and as always, remember, don't just fly, climb to the flight levels. If you enjoyed this video, click here to check out my video about how air traffic controller schedules work. You're gonna love it.